So we've seen this picture before. There are two examples on your page. We're going to talk about where this function, we'll call it f of x, is not differentiable. And so you have that formal definition, which is really good, and you have this, that sort of informal definition in your mind. A couple things we're going to check even before we think about those. You could say that f of x is not differentiable at x equals -1 because f of x is not continuous at x equals -1. So before we even worry about whether the slope from the left equals the slope from the right, we have to worry about whether the function is even continuous. And I say we have to go even one step before that and notice that f of x is not even defined at the place where x equals -1. There's no colored in dot at x equals -1. So never attempt to evaluate, to find a derivative and then figure out what the value of the derivative is at a place where the original function wasn't even defined. It's not going to happen. So this is my answer. F is not differentiable at x equals -1 because f is not defined at x equals -1. The next place, I'm just going to go from left to right. The next place where I notice a problem is at x equals 0. What's the problem at x equals 0? Well, f is not continuous at x equals 0, so there's no way we're going to be able to find the derivative. I'll write that up for you. I'll just clarify what I wrote. I said f is not differentiable at x equals 0 because f is not continuous at x equals 0. And if I'm going to be justifying all my answers, I have to justify my decision that f is not continuous at x equals 0. So notice I have to write my notation a little bit funny just because of the option on my software here. So the limit as x approaches 0 of f of x, which is 2, right, is not equal to f of 0, which is whatever the y value at that dot is. Okay, the next place I'm going to look is at x equals 1. Here's my first chance to bust out my new knowledge. F is totally continuous at x equals 1. I could draw the function without picking up my pencil at f equals 1. And right there at x equals 1, the limit exists. It's whatever that y value is. And that's the dot that got colored in. So the function value is equal to the limit. So this is not a problem of continuity. This function is continuous. But what is my problem? My problem is that as I approach x equals 1 from the left, I have a slope, I have a derivative that nobody filled in a y value for that top point. So I'm not going to be able to figure out the slope exactly, but I can tell this function's going uphill, so the slope must be positive. And as I approach from the right, the derivative must be negative because the function starts going downhill. So I'm going to write that up formally for you, and it's going to be a little funny because I'm going to have to draw the notation with my finger, but this is what I would write up for at x equals 1. So I'll read this for you, and I appreciate your patience with as the technology catches up with us. So I would say f is not differentiable at x equals 1 because the limit as x approaches 1 from the left of f of x minus f of 1 over x minus 1 is not equal to the limit as x approaches 1 from the right of f of x minus f of 1 over x minus 1. Notice that's the definition of differentiability that we wrote down before, except everywhere I had a before, I've now replaced it with my a value in this case, which is 1. So what does this mean? This means that the slope from the left, the slope as you approach x equals 1 from the left, does not equal the slope as you approach x equals 1 from the right. This is a formal justification for why this function is not differentiable at x equals 1. Now, that's great. You'll need to know this and use it on the free response section. What if it's the multiple choice section and all you have to do is try to figure out, I don't know, an x value where this function is continuous but not differentiable? Well, you would look at all the places where it's continuous, and probably what's going on in your mind is like, okay, well, I'm going to check for those things that we said are places where a function is not differentiable: corner, cusp, vertical tangent, and discontinuity. So you are probably thinking to yourself, oh, there's a corner there, it's not differentiable. That's great. That is all you would need to do in the multiple choice section. But that's an informal justification. If you need to bust out a formal justification, it's this one, which we wrote down on the other side of this paper. I think there's one more answer for this question, which is at x equals 2, f is not differentiable because f is not continuous at x equals 2. If I were going to specify, if I was going to justify my decision that f is not continuous, I'm going to refer to the definition of continuity. So I'd say the limit as x approaches 2 of f of x does not exist. And notice that this notation I've used, that's how we read it, but normally this x as x approaches 2 should be a little subscript. It just doesn't work on my computer. Okay, so we're going to look at this next example. All right, so example 2, I have a piecewise defined function and I have 2 questions on the board. Question number 1, is f continuous at x equals 3? That's a question we could have answered last chapter, but why are we asking it? Because we know we don't even want to bother trying to figure out if f is differentiable at x equals 3 if we find out it's not continuous. So once we decide whether f is continuous, if we decide it is continuous at x equals 3, then we're going to try to answer this question, is it differentiable? So remember our definition for continuity. F of x is continuous at x equals 3 if the, there we go, if the limit as x approaches 3 of f of x equals f of 3. Well, and the limit is only going to exist if the limit from the left equals the limit from the right. So we're going to need the left-hand limit and the right-hand limit. One of those will also be the function value. So we're going to just make sure that those 3 things are all equal. So if I let x equal 3, then the limit from the left, I'm going to use that rule. The limit as x approaches 3 from the left of f of x is 3 squared, which is 9. I used that top rule because that's the rule that's active for numbers x values that are less than 3, and that's what's going on. Those are what x values I'm using as I approach 3 from the left. Now I need the limit as x approaches 3 from the right of f of x. That's going to be 6 times 3 minus 9 is 18 minus 9, which also equals 9. And it turns out the function value I'm going to get from using that same second rule, because that's the rule that has the or equal to sign for the domain. So I do find out that the limit from the left equals the limit from the right, which is equal to the function value. So I conclude that f is continuous at x equals 3. So just to clarify, that's how I would justify my first answer. F is continuous at x equals 3 because the limit as x approaches 3 of f of x equals f of 3. So my next question, now that I know f is continuous there, I can start to think about whether it's differentiable there. Is f going to be differentiable at x equals 3? Well, what am I going to check? I'm going to have to check the limit as x approaches 3 from the left of f of x minus 3 over x minus 3, which is another way of saying the derivative from the left. I'm going to have to check the derivative from the right. I'm going to check that they match. So let's do the easy one first. Notice my second rule. I'm going to get the other stuff out of the way here. You've seen that justification. Okay. As I approach x from the right, I'm starting with this one because this function rule is linear. And we have this nice chill way of figuring out what the derivative of a linear function is. Derivative is slope. Slopes of linear functions are constants. So I would say that the limit as x approaches 3 from the right, that's the right, of f of x minus f of 3 over x minus 3 is the slope of this function, the derivative, as I come from the right, is going to be the slope of that line, which is 6. Okay, well that's good. So now I'm hoping that the derivative from the the derivative from the left is also going to equal 6. So what am I going to do? I'm going to bust out my definition. I'm going to take the limit as x approaches 3 from the right. This is going to be f of x minus f of a. Oops, but we know a is 3 over x minus 3. Well, what do we have here? That's the limit as x approaches 3 from the right? F of x is x squared minus f of 3 is going to be 3 squared, which is 9, over x minus 3. Okay, so we've seen problems like this back in our 2.1. So I can't replace x with 3 because I'm going to have a 0 in the denominator problem, but I can factor and cancel. X squared minus 9 is x plus 3 times x minus 3. The x minus 3's are going to cancel, and I'm going to get the limit as x approaches 3 from the right of x plus 3. Check this out. No more divide by 0 problem. Replace x with 3. 3 plus 3. The derivative of f as I approach 3 from the right is 6. So my derivative from the left and my derivative from the right, both 6. The one-sided derivatives match. A function is continuous, so I conclude that yes, f is both continuous and differentiable at x equals 3. So I'll move me out of the way, and you can see what your textbook assignment is on page 114. Remember, there are 2 sets of problems on that page. There's the quick review. This is not what I'm talking about. I'm talking about the section 3.2 problems, so 8, 39, 40, 41, and 44.